Hey, you. Ever wonder what numbers really are?
Hmm.
Well, today we're going to take a deep dive into Bertrand Russell's Introduction to Mathematical Philosophy.
Oh, excellent choice.
Yeah, and hopefully figure that out.
Yeah.
We've got excerpts from his preface, table of contents, and some key chapters.
Okay.
Hopefully, it's enough to give us that aha moment about how math and logic are all intertwined.
You know what's so intriguing about this book is that Russell really wants to make this accessible,
Okay.
even if you don't speak logic fluently.
Right.
He intentionally left out the super complex stuff from his other work, Principia Mathematica.
So it's like mathematical philosophy, the Cliff Notes version?
Exactly, yeah.
I appreciate that.
Okay.
In the preface, Russell uses this analogy
Okay.
about exploring the world of math, that you need both a telescope and a microscope.
Oh, interesting.
What's that all about?
Well, he's saying you need the big picture view, right?
Okay.
Like seeing how vast the number system is.
Right.
But also the close-up to examine the tiny details of how those numbers work.
Yeah.
It's not enough to just know the rules.
Uh-huh.
We need to understand the why behind them.
I'm starting to see why this is philosophy
Yeah,
and not just a math textbook.
absolutely.
So where does Russell start his exploration?
Well, he starts with a seemingly simple question.
Okay.
What is a number?
Okay.
Right? We use them all the time.
Yeah.
But rarely stop to think about what they truly represent.
Hmm.
And Russell argues that actually the usual definitions are either circular or incomplete.
I'll admit, I haven't given it much thought.
Sure.
Numbers just are.
Yeah.
What's so complicated about that?
Well, think about it. Like if you try to define 2,
Right.
you might say, well, it's 1 plus 1.
Okay, yeah.
But then what's 1?
Right.
You're defining a number using other numbers.
Yeah.
So Russell wanted a definition grounded in logic,
Okay.
and that led him to focus on plurality.
Plurality. So like the idea of multiple things existing.
Exactly, yeah.
Okay.
So he uses logical classes and relations to define plurality instead of just saying 2 is a symbol.
Right.
He says it represents the class of all pairs.
Okay.
So your 2 hands,
Uh-huh.
2 stars in a binary system, they all belong to this class of onenesses
Yeah.
because of their shared relationship.
Okay, so it's not just about the number itself,
Right.
the relationship between things.
Yes.
That makes them 2 or 3 or whatever number.
Exactly.
That's actually pretty deep.
Yeah.
Does this plurality idea work for all numbers then?
It's the foundation, right?
Okay.
But to build up the whole number system, Russell uses a tool called mathematical induction.
Yeah.
And it's this idea that if something is true for the first number
Okay.
and true for any number and the next one after it,
Okay.
then it's true for all the numbers in that sequence.
I vaguely remember that from math class.
Right.
It felt like magic.
It's a powerful tool for explaining how we get from 0 to infinity. And Russell uses it to define natural numbers,
Word.
showing that each one is built by adding 1 to the one before it.
Right.
And because this is rooted in logic,
Yep.
it helps bridge the gap between finite numbers and the infinite.
So he's not just defining what numbers are,
Right.
but how they relate to each other in a logically sound way.
Exactly.
This is making me see the order behind the numbers.
Yeah.
Like they're all connected by invisible threads of logic.
That's precisely the point.
Okay.
And these threads are what Russell calls relations.
Okay.
He dedicates a good chunk of the book to explaining different types of relations
Uh-huh.
and their importance in building up mathematical concepts.
Wait, are we talking about simple relations?
Well,
Like bigger than or smaller than?
yeah,
Because it doesn't seem very philosophical.
it's deeper than that.
Okay.
He categorizes relations in various ways.
Okay.
For example, asymmetrical relations
Mm.
are like parent of,
Okay.
right? You can't reverse it.
right.
The child isn't the parent of the parent,
Right.
but sibling of is symmetrical.
Yeah.
The relationship goes both ways.
Okay, I'm starting to see how this gets complex.
Yeah.
But how do these different types of relations actually matter for understanding numbers?
Well, they're crucial for understanding order and series,
Okay.
which are fundamental to mathematics.
Right.
So take the natural numbers, 1, 2, 3, and so on.
Okay.
The successor relation is asymmetrical.
Okay.
2 follows 1, but 1 doesn't follow 2, right? This creates a clear direction,
Yeah.
like a one-way street for counting.
So without those carefully defined relations,
Yeah.
the whole number system would be chaotic.
It would be a mess.
It's like he's showing us the traffic rules that keep everything flowing in the right direction.
Exactly, yeah.
And this meticulous examination of relations
Right.
is also how he tackles those rule breakers of the number world. Irrational numbers.
Oh, yeah, good point.
Ah, yes, those pesky numbers like pi and the square root of 2
Right.
that never quite fit in.
Exactly.
What does Russell say about them?
Well, he explains how irrational numbers challenge traditional math
Okay.
because they couldn't be expressed as simple fractions,
Right.
which was mind-boggling for a long time.
Yeah.
So Russell dives into what are called Dedekind cuts to show how they fit in.
Dedekind cuts.
Yeah.
That sounds intimidating.
It's a funny name.
Can we get the explain it like I'm 5 version?
Sure, so imagine cutting a cake perfectly in half.
Okay.
A Dedekind cut divides the rational numbers on a number line
Okay.
into two groups,
Okay.
those smaller than the cut and those bigger.
Got it.
Now, for rational numbers, the cut lands right on a number.
Okay.
But for irrational numbers,
Yeah.
it falls in a gap between the rationals.
Okay.
And that defines the irrational number by where that cut is.
So it's like saying an irrational number is defined by what it isn't,
Yes.
by the space it occupies between the rational numbers.
Exactly.
That's a neat way to visualize
A
it.
very visual way of thinking about it.
Yeah.
And it's a way to integrate those kind of like rebellious numbers into the system.
Uh-huh.
And this leads to the concept of real numbers, which
Right.
includes both the rationals and irrationals,
Right.
creating a more complete number landscape.
So he's systematically building up our understanding of numbers.
Yes.
Step by step, from
Uh.
basic logic to these more complex categories.
Absolutely.
But where do complex numbers fit in?
Oh, that's a good question.
Those always seem like mathematical unicorns to me.
They do seem a bit mythical at first.
Right.
So complex numbers, with their square roots of -1,
Yep.
initially emerged as solutions to certain equations.
Right.
But Russell explains how they can be rigorously defined as pairs of real numbers,
Okay.
one representing the real part and the other the imaginary part.
So instead of just manipulating these strange numbers based on rules,
Yeah,
he's giving them a solid logical foundation.
exactly.
It's like he's taming the mathematical wilderness.
He is. He's bringing order to the chaos.
And I have a feeling things are about to get even wilder
Oh, yeah.
as we delve into infinity in the next part.
Buckle up.
Yeah.
Because we're about to explore infinite sets and transfinite numbers,
Okay.
concepts that will truly challenge your understanding of what's possible in mathematics.
Okay.
Yeah.
I'm ready.
All right.
All right, we built up a pretty solid understanding of different types of numbers.
Yeah.
All thanks to Russell's logic-driven approach.
It's a good foundation.
But now let's talk about infinity.
Okay.
It's a concept that's always kind of fascinated me,
Right.
but also terrified me in equal measure.
Yeah, it's a bit mind-boggling.
So how does Russell even begin to tackle that mathematically?
Well, he starts by distinguishing between finite and infinite numbers.
Okay.
And remember that powerful tool we talked about, mathematical induction?
Yeah.
Well, he defines finite numbers as those that you can reach
Okay.
by starting from 0 and repeatedly adding 1, just like we did before.
Right. So finite numbers are the ones that play nicely with mathematical induction.
Exactly.
What about infinite numbers? Do they just refuse to follow the rules?
You could say that they don't fit neatly into that framework.
Okay.
So to describe them, Russell introduces this concept of reflexive classes and numbers.
Reflexive, like looking in a mirror.
Yeah.
How does that relate to numbers?
Well, it's a good analogy, actually.
Okay.
A reflexive class is one that can be put into a one-to-one correspondence with a part of itself.
Hold on. How can something be the same size as a part of itself?
Right.
That seems logically impossible.
It's a paradox.
Yeah.
But it's key to understanding infinity.
Okay.
So consider the set of all natural numbers, 1, 2, 3, and so on.
Okay.
Now think about just the even numbers, 2, 4, 6, and so on.
Okay.
You can pair each natural number with its double,
Right.
creating a perfect one-to-one match between the whole set and a subset.
So even though the set of even numbers seems smaller,
Right.
it actually contains the same number of elements
Exactly.
as the entire set of natural numbers.
Yeah, that's infinity for you.
That's messing with my brain.
It breaks our usual ideas about arithmetic, like you can subtract a finite number from infinity and still have infinity.
Right.
You can even divide infinity by a finite number
Yeah.
and still get infinity.
Right.
It defies our everyday logic.
This is where I usually tap out when it comes to math.
Okay.
But I'm curious, how does Russell actually work with infinity
Yeah.
if it's so counterintuitive?
Well, he introduces the concept of infinite cardinal numbers
Okay.
to measure the size of infinite sets.
Okay.
Now, they work differently from regular numbers,
Okay.
but they help us compare different levels of infinity.
Wait, different levels of infinity? You telling me some infinities are bigger than others?
Exactly. It's a mind-blowing concept.
Yeah.
But it makes sense when you think about it.
Okay.
So the set of natural numbers has a cardinality,
Okay.
represented by LF null,
Okay.
which is denoted as EDEF,
Okay.
and it's the smallest infinity.
So LF null is like the starting point for infinity.
You could say that
Okay.
any set that can be put into a one-to-one correspondence with the natural numbers
Okay.
also has cardinality aleph null.
All right.
That includes even numbers, odd numbers, even all the rational numbers.
So even though there are infinitely many fractions between each whole number,
Right.
the set of rational numbers is still the same size
Exactly.
as the set of natural numbers.
That's right.
Infinity is wild.
It really is.
But it gets even wilder.
Oh, yeah.
The set of real numbers,
Right.
which includes both rational and irrational numbers,
Yeah.
has a cardinality larger than Aleph null.
It does.
How can one infinity be bigger than another?
Right.
It feels like we're breaking the rules of reality.
We are going beyond everyday intuition here.
Okay.
So to explain this, Russell dives into the concept of power sets.
Okay.
A power set is the set of all possible subsets
Okay.
of a given set.
Okay.
And he shows that the power set of a set
Yeah.
always has a greater cardinality than the original set,
Okay.
even for infinite sets.
So the set of all subsets of the natural numbers
Yes,
is actually bigger than the set of natural numbers itself.
precisely.
Wow.
And the set of real numbers
Okay.
has the same cardinality as the power set of the natural numbers,
Okay.
which is represented by 2 raised to the power of Aleph null.
My head is spinning. These are some seriously abstract concepts.
That's the beauty of exploring infinity. It pushes the limits of our understanding.
Okay, so to navigate this strange world,
Right.
we need to talk about the multiplicative axiom.
Yes, exactly.
Okay, hold on.
Yeah.
We've got cardinal numbers,
Right.
power sets,
Uh-huh.
and now the multiplicative axiom.
Yeah.
My brain needs a break.
Okay, well, in simple terms,
Okay.
this axiom deals with choosing elements from sets.
Okay.
It says that given any collection of non-empty sets,
Okay.
you can always pick one element from each set.
Sounds obvious.
Right, if I have a bunch of bags,
Yeah.
each with at least one marble,
Yeah.
I can always choose one marble from each bag.
What's so complicated about that?
Well, it gets tricky with infinite sets.
Okay.
The act of making infinite choices can have some mind-boggling consequences.
Okay.
So this axiom underpins a lot of mathematical concepts,
Uh-huh.
but it also leads to some strange paradoxes.
Paradoxes. Now you've really got my attention.
Okay, so one famous consequence is the Banach-Tarski paradox,
Okay.
which suggests that you can theoretically cut a sphere
Okay.
into a finite number of pieces
Okay.
and reassemble those pieces into 2 spheres,
Wow.
identical in size to the original.
Wait, that's impossible.
Right.
You can't create something out of nothing.
It highlights the weirdness of infinity
Yeah.
and the consequences of the multiplicative axiom.
Okay.
So the paradox hinges on decomposing the sphere
Yeah.
into such bizarre and unmeasurable sets of points
Okay.
that they defy our usual notions of volume.
It feels like we're bending the rules of reality.
That's what makes exploring infinity so fascinating.
So another important axiom related to infinity
Yeah.
is the axiom of infinity itself.
Yeah, that's right.
Okay, we've got the multiplicative axiom,
Right.
now the axiom of infinity.
Yeah.
My brain needs a break.
All right, well, simply put,
Okay.
it asserts that an infinite set exists.
So even the existence of infinity needs a logical proof.
Exactly. In logic, you can't just assume things.
Okay.
So Russell illustrates the importance of this axiom
Okay.
with a thought experiment.
Okay.
Imagine a world with only 9 individuals.
A world with only 9 people. That sounds incredibly lonely.
It would be.
Yeah.
It would also lead to some strange mathematical problems.
Okay.
So in this world, you could count up to 9.
Yeah.
But the succession of 9, which we'd call 10,
Right.
wouldn't exist
Because there are no more people.
because there are no more individuals to count.
Okay.
So every number after 9 would just be an empty set.
So it's like hitting a mathematical wall.
Exactly. Russell calls this an arithmetical catastrophe.
An arithmetical catastrophe. I like
Yep.
that. So the axiom of infinity prevents these catastrophes.
It does.
By guaranteeing there's always an X number,
Yeah,
even when dealing with these infinitely large numbers.
exactly.
Wow, these axioms might seem simple,
Right.
but they have huge implications
They do.
for the whole structure of math.
Yeah,
It's amazing how much thought goes into
right.
making sure the system is logically sound.
It all goes back to Russell's goal
Okay.
to show that traditional pure mathematics can be derived from natural numbers
Okay,
and that natural numbers themselves can be reduced to logical principles.
so he's saying math isn't some arbitrary set of rules.
Right.
It's a direct expression of logic.
Precisely.
This connection between math and logic
Yeah,
has profound implications for how we view mathematical truths.
absolutely. But that's a discussion for our next and final part.
I can't wait.
Okay.
This journey into infinity has been mind-blowing,
Good.
but I'm ready to tackle the philosophical side of things next.
All right. Sounds good.
Welcome back. We've journeyed through the foundations of numbers.
It's been quite a journey.
Yeah,
Yeah.
and we even tackled the wild world of infinity.
A bit mind-bending.
Yeah, all thanks to Bertrand Russell's insightful approach and introduction to mathematical philosophy.
He's a great guide.
Now let's get to the heart of the matter,
Okay.
the philosophical implications of all this.
All right.
After seeing how meticulously Russell builds up math from basic logic,
Yeah.
I'm really curious, what does he say about the nature of mathematical truth itself?
That's the big question that Russell is grappling with.
Okay,
He argues that mathematical truths are essentially logical truths,
Okay.
what we call tautologies in philosophy.
Tautologies, that rings a bell from my logic class.
Yeah.
It's like saying a circle is round or all bachelors are unmarried.
Right.
Those statements are true by definition.
Exactly.
But they don't really tell us anything new about the world. Is Russell saying math is just a bunch of fancy tautologies?
Well,
That seems kind of disappointing.
it's not quite that simple.
Okay.
While mathematical truths are tautological,
Okay.
in the sense that they follow logically from their premises,
Okay.
those premises themselves aren't arbitrary. They're
Right.
carefully chosen to reflect our basic understanding of the world,
Okay.
especially how we grasp sets and their relationships. Remember those logical classes that we talked about?
Uh-huh.
They're the building blocks.
So it's like math is a language we've constructed to
Yeah.
describe the structure of reality.
Okay.
And the truth of mathematical statements
Yeah.
comes from how well they fit within that language.
That's a great way to put it.
Okay.
Is what Russell called the logicist view of mathematics.
Okay.
And he believed that all mathematical concepts
Okay.
could be defined using logical concepts.
Okay.
And all those theorems and proofs that we learn
Yeah.
are ultimately derived from logical axioms and rules.
So this makes me wonder, if math is really just logic in disguise,
Huh.
does that mean mathematical truths are absolute and unchanging?
Right.
Like, are they independent of human minds and how we perceive the world?
That's a deep philosophical question
Right.
that's been debated for centuries.
Yeah.
And Russell himself wrestled with this idea
Okay.
of whether mathematical truths are discovered or invented.
Okay.
His logicist view leans towards discovery,
Okay.
implying that math reveals something inherent in the structure of logic itself.
So even if there were no humans around
Right.
to think about numbers and equations,
Yeah.
those mathematical truths would still exist out there
Right.
in the realm of pure logic.
Yeah.
Like pi would still be an irrational number,
Uh-huh.
even if no one was around to calculate it.
That's the implication of Russell's view.
Wow.
He saw mathematics as unveiling a profound,
Okay.
timeless, and objective order within reality, something that exists independent of our minds.
It is a pretty awe-inspiring idea,
Yeah.
but part of me still wonders if maybe math is more of a human creation.
Okay.
A tool we've developed to make sense of the world, rather than some absolute truth we're uncovering.
That's a valid perspective, too.
Okay.
There are other philosophical schools of thought,
Right?
like formalism and intuitionism,
Okay.
that challenge the logicist view.
Okay.
They suggest that math might be more about human conventions
Okay.
and the systems we create
Yeah.
than about discovering universal truths.
It's amazing how diving into the world of numbers and logic
Yeah,
leads to such profound philosophical questions about truth,
right.
reality,
Yeah.
and even what it means to be human.
It really expands our thinking.
Bertrand Russell's Introduction to Mathematical Philosophy has certainly been a mind-bending experience.
He's a challenging thinker.
Yeah, he's challenged my assumptions about numbers,
Yeah.
infinity, and the very basis of mathematical thought.
Yeah.
What's the key takeaway you hope listeners will walk away with from this deep dive?
Well, I hope this exploration has sparked a sense of wonder and curiosity about the interconnectedness of math and logic.
Yeah?
I think Russell's work shows us that even the most abstract concepts
Yeah.
are rooted in these fundamental principles of reasoning,
Right?
and it encourages us to think critically
Okay.
about the ideas we often take for granted,
Yeah.
and it reveals the hidden depths beneath the surface
Okay.
of what we might consider simple math.
It's definitely left me with more questions than answers.
That's good. That's a sign of a good deep dive.
But in the best way possible,
Yeah.
I'm inspired to keep exploring these ideas further.
Excellent.
Any final thoughts for our listeners before we wrap up?
Well, if math truly is an extension of logic, as Russell argues,
Okay.
could there be other equally valid systems of mathematics built on different logical foundations?
Okay.
Could these alternative systems lead to different conclusions about the nature of reality?
That's a really thought-provoking challenge.
Yeah, it's something to ponder.
I think I'll need some time to contemplate that one.
Okay.
A huge thank you to you for being such a fantastic guide on this incredible journey.
It's been my pleasure.
And to all our listeners, thank you for joining us on the Deep Dive.
Yeah, thanks for listening.
We'll be back soon with another deep dive into a new topic, ready to uncover more hidden gems of thought and knowledge.
173A?